Simulated annealing is a powerful problem-solving technique used across computer science, engineering, AI, and optimization. It finds excellent solutions to complex problems with numerous possibilities where identifying the best choice is challenging. This technique draws inspiration from metallurgy, where metal is heated and slowly cooled to strengthen its internal structure. In optimization, our goal is similar: to discover the best possible solution among many options. However, for many real-world challenges, the sheer number of potential solutions is astronomically large, making exhaustive searching impractical. Simulated annealing provides a clever method to explore these possibilities efficiently, helping us avoid common pitfalls and local traps. The term annealing originates from materials science, where heating metal or glass to high temperatures allows its molecules to move freely. Slow cooling then enables these molecules to settle into a stable, robust structure. Conversely, rapid cooling can lead to a brittle or weak material, as molecules become locked into a suboptimal arrangement. Simulated annealing applies this very concept to finding solutions. Here, heat symbolizes randomness or broad exploration, and cooling signifies the gradual reduction of this randomness, guiding the algorithm towards a stable solution. Initially, the algorithm is free to explore many different solutions, even those that might appear less optimal. As time progresses, it slowly reduces this randomness, becoming more selective, and eventually converges on a good, ideally the best, solution. Many optimization problems present rough landscapes, which can be visualized as a terrain of hills and valleys. Each point on this landscape represents a possible solution, and the height of the land indicates its quality. Our objective is to locate the lowest valley, representing the optimal solution. However, much like hiking in dense fog, it's easy to become trapped in a shallow dip, mistakenly believing it's the lowest point. A simple method like hill climbing would merely descend and stop at the nearest low point, missing those deeper, more optimal valleys. Simulated annealing overcomes this by occasionally permitting moves that go uphill, meaning it sometimes accepts a slightly worse solution intentionally. This strategic allowance helps the algorithm escape shallow traps and continue its quest for superior solutions. Let's conceptually break down how simulated annealing works. First, you begin with an initial solution, which can be entirely random or an educated guess. Next, you evaluate the quality of this solution using metrics like cost, score, distance, or time. Then, a small modification is made to the solution, like adjusting a single detail to see if improvements occur. The algorithm then decides whether to accept this new solution. If it's better, it's accepted. If it's worse, it might still be accepted, especially early on when the temperature is high. Gradually, the temperature is reduced. This means the algorithm explores widely at first, then refines its search. Finally, the process stops when the system is cooled, having settled on a stable solution. This approach allows for broad exploration initially, followed by careful refinement over time. Simulated annealing is invaluable in situations where problems are difficult to solve due to an overwhelming number of possible combinations. In scheduling, it helps assign workers to shifts, schedule airline crews, and create school timetables, balancing needs and avoiding conflicts. For route optimization, it guides delivery trucks in planning efficient routes and robots in warehouses, reducing fuel, time, and cost. In engineering design, it's used for designing computer chips and laying out electrical circuits, minimizing interference and maximizing efficiency. Within machine learning, it tunes model parameters, helping to escape weak solutions early and refine better ones later. In finance and economics, it aids in portfolio optimization and risk balancing, exploring trade-offs between return and stability. One of its key strengths is its ability to escape local traps by occasionally allowing moves that seem worse. It's also conceptually simple, making it easy to understand and implement. Furthermore, its versatility allows it to work effectively on many types of optimization problems. It doesn't even require perfect data, performing well even when models are unclear. While simulated annealing doesn't guarantee the absolute perfect answer every time, it consistently finds a very good answer efficiently. This efficiency is often more valuable than waiting indefinitely for a theoretically perfect, but practically unattainable, solution. However, it can be slow if not tuned correctly, and choosing the right cooling schedule is crucial. Also, results can vary slightly across runs due to its inherent randomness. Nevertheless, with well-chosen parameters, it performs strongly in many real-world applications. In summary, simulated annealing is a problem-solving technique inspired by the heating and cooling of metals. It helps find good solutions to complex problems by exploring widely at first, then gradually narrowing its focus. Unlike rigid methods, it sometimes accepts worse solutions early on to escape traps and discover better ones later. This makes it incredibly useful in scheduling, routing, engineering, machine learning, and finance. Anywhere complexity makes finding the best solution difficult. In simple terms, simulated annealing solves hard problems by exploring freely first, then tightening carefully, just like cooling metal to make it strong and stable.